Hey everybody, we're going to start the show in about 5.5 minutes, and if you can hear me, say so in the chat. You are actually seeing a live view of Earth's moon from our big South Dome main facility telescope. Hi there. Hey everybody, welcome to episode number 13 of Goldendale Observations, the Exoplanet episode. This is an episode I've been looking forward to putting on because I happen to find the topic of exoplanets interesting, even exciting. We live in an astonishing time where we can actually confirm their existence and study them. In case this is your first visit to Goldendale Observatory virtually via the wonders of the internet, this facility is brand new. We upgraded dramatically over the last few years. We have about 3 times the space. We have more high technology, including fast internet, which allows us to put on remote shows like this. Because this is a public educational facility, we want you to learn stuff, so please, please, please ask questions during the show or make comments. We will see the chat. We do have chat moderators filtering the chat, so hopefully I'll get to all your questions tonight and maybe even your comments. I mentioned that I find exoplanets interesting. I love the fact that we get to talk about this with young people who are being born into a world where we know that exoplanets exist. Before I get into the science and the nitty-gritty of this topic, I want to share with you a little story from my childhood. I remember when I was a kid, and I would watch science fiction movies, or I would read science fiction books, and constantly, any space-based science fiction story would imply that the universe was full of planets. And our heroes would wander from star system to star system, landing on these places. They actually walked around and explored these bodies, many of which were Earth-like, imagine that. And as a kid, I didn't think anything of it. I took it for granted. It became completely normalized to me. But as I got older, I realized it seemed a little silly. It seemed a little bit presumptuous. Because as I grew older and began to study science more formally, I realized that we had no evidence for the existence of exoplanets. That doesn't mean we didn't think they existed, but we didn't know of any. Or if we did, we knew of a very small number for extraordinary reasons that existed in bizarre solar systems. So it didn't seem that the science fiction prediction was playing out, a universe full of Earth-like planets. But then things started to change. We started constructing telescopes and spacecraft designed to look for exoplanets, and we started finding them. And suddenly, science fiction didn't feel so fictional anymore. I remember in the late 90s going to see Star Wars, The Phantom Menace, the first of the prequel movies, and laughing during a little exchange between Anakin Skywalker and Jedi Master Qui-Gon Jinn, where they're looking up at the stars, and Anakin goes, "Do they all have a system of planets?" And Qui-Gon goes, "Most of them." And I snickered because I'm like, yeah, right. It turns out I shouldn't have been so pessimistic or cynical, because it turns out, yes, indeed, it seems now evident that having planets is something that stars do. It is normal, ordinary, regular, expected for a star to have planets around it. We're going to talk a little bit about how we know that during this presentation. We'll also talk about actual details of those planets and the star systems they inhabit. And hopefully by the end of this, you'll have a good idea of what exoplanets are, where they are, what they're like, and how we find them. And be aware, this is cutting-edge science. We have a long way to go. We've essentially just started down this long journey. So, again, an exciting time because we can convey to young people that they do indeed live in a universe full of planets. Whereas, when we were kids, we didn't know that. We assumed it, but we didn't know it, and now we do. So, I'm going to get into the science of it a bit. In case I didn't identify myself, my name is Troy Carpenter, and I've been here at Goldendale Observatory for almost 8 years. And this virtual presentation format is something we did plan on doing before the virus happened, but now we do it every single week. I'm learning to adapt to this process. And I can tell you on a personal level, I enjoy this process a lot more if you guys interact. So please ask questions or make comments. On that subject, let's see if we have any questions already. I see someone has asked, are there things unique to some solar nebulae that may lead to the creation of solar systems with exoplanets? Yes, and that's actually a good question. As the universe ages, it becomes more chemically enriched. And we assume that a star system needs to be metal-rich in order for it to have exoplanets. However, we have now discovered exoplanet systems that are not high metallicity. So it turns out perhaps, again, we were too cynical, perhaps too pessimistic. It turns out you may not need to have a metal-rich nebula collapsing to provide planets, which isn't that surprising when you consider that gas giants are the same thing stars are, giant balls of hydrogen and helium, and hydrogen and helium are not considered metals by astronomers. So the answer is, we used to think that you needed to have a metal-rich solar nebula to give rise to planets. Turns out that may not be the case after all. By the way, again, that's an example of a recent discovery. It wasn't that long ago. In fact, it was announced this year that we found a star system, a solar system, with planets, or at least a planet, orbiting a population 2 star. Now, you guys might remember from a previous show, we talked about the fact that there are 3 generations of stars, and we named them backwards. So the youngest generation is known as population 1, and the oldest generation, the very first stars, are called population 3. We somewhat dogmatically assumed, like I mentioned, that you had to have a population 1 system, a metal-rich system, to have planets. But the one that was recently announced actually is a planet orbiting a population 2 star. That planet is over 10 billion years old. That's a very big discovery. Keep that in mind. Oh, good. Someone even brought it up. That's good. Someone actually identified it. Thank you. Troy, where did you work before Goldendale? I've done a lot of things. I don't like to talk about my career. I ran a training center in Philadelphia, among other things, and I worked in the power generation sector. I also lectured on energy economics, electrical theory, electrical safety, all kinds of technical stuff. Before that, I worked in broadcasting. I've done a lot of things. Please don't try to replicate my career path. It's a very peculiar story, and I don't recommend it to anyone because it may not work out so well. We'll see, though. Speaking of things working out, a lot of people don't realize that thanks to the internet, you can learn a great deal about what used to be considered advanced topics like astronomy from the comfort of your chair or bed. Sometimes at night I'll be in bed just reading space stories, science articles. That's remarkable. So you don't necessarily have to be a formal student of astronomy to learn a great deal about it. I would like to think that shows like the one you're watching right now are examples of that fact, because during this presentation I encourage you to ask advanced questions if you have any, and we'll get to them. You don't actually necessarily have to go to college if you want to learn a whole bunch about astronomy. By the way, that's new. That is a new development in the history of humanity, the fact that we now have the ability to learn things without, being rich or knowing the right person, getting a special grant from the king or something like that. It's remarkable that regular folks can learn about things like neutron stars and supernovae, and in this case, exoplanets. That didn't used to be the case. It used to be the only access you had to astronomy was knowing like the amateur astronomer down the street. If you lived next to a guy with a telescope, that was your only experience, your only exposure to telescopes. By the way, that's one of the cool things about Goldendale Observatory. Being a public facility, we encourage people to come and look through our giant telescopes when we're open. Speaking of which, I hope you enjoyed that little view of the moon. Let me go back to that real quick. There it is. Just briefly, I'm not going to leave this on the screen because the show's not about the moon tonight, but this is indeed a live view from our south dome. And it's coming from the 6-inch refractor mounted to our 24.5-inch Newtonian telescope. And I want you to notice the wiggling and the wobbling. That's how you know it's video and not a photograph. And of course, that's Earth's atmosphere. Let me zoom in here a little bit. See the wiggling and the wobbling? All that motion is being caused by that pesky atmosphere, which ruins our fun. That will come up a bit during our presentation tonight, because, as always, atmosphere complicates astronomy. And things like hunting for exoplanets is made more difficult. Tasks like that are made harder by the effects of Earth's atmosphere. You're going to learn more about that tonight. All right. Let's get right down to it. Looking at the chat here. What makes Goldendale Observatory unique? I mean, this is going to sound like a joke, but the fact that it exists is what makes it unique, and I say that because it was placed here for peculiar reasons. And we're actually going to do an episode in the next week or two about the history of the place a little bit and its connection to the convergence of 3 solar eclipses, which all occurred in this area in less than 1 century of time. You probably remember the most recent one that was in 2017. So, also the fact that a famous experiment was conducted here in Goldendale attempting to prove Einstein's relativity. Contrary to popular myth, they did not prove relativity here, but they did attempt to by imaging stars near the sun during a solar eclipse and looking for the gravitational lensing effect of the sun's gravity bending the starlight. That is not a tangent, and that is something that's going to come up in our show tonight. Hold that thought. Okay, where to start? Where to begin? Can I recommend an app to learn about stars? You know, it's funny, there's so many now. I can't. And a lot of people use Apple products. I have Android, and so I've noticed a lot of the ones I recommend are not on Apple. I recommend you go to your app store and search for planetarium or astronomy, and then sort by score, and maybe you'll find some good stuff. You'll find that people do a pretty good job of reviewing the quality of those apps. One I like to use that I actually enjoy very much is called Mobile Observatory. It's not free though. I think it's $5. It's well worth the $5. But if you're a casual, if your interest is casual, you may not want to spend any money up front. There's plenty of free ones too. Okay. Will there be any more live views of the telescope? Not tonight, but we will do those. In fact, I'd like to start a tradition where I show you the moon every night I can when it's clear and when the moon is out. Of course, that's weather dependent. And that's one of the reasons we haven't been doing it very much. This time of year, we have a lot of clouds. And I was happy to actually see the moon, and that's why I was like, oh, I have to take advantage of this opportunity. So I did. Okay, let's start with definitions. You guys need to add a word to your vocabulary. You should incorporate this into your personal lexicon, because this word is not going away. And that word is exoplanet, which is kind of short for extrasolar planet. And there is some confusion about what constitutes an extrasolar planet. Essentially, it's a planet that orbits another star. Now, there are planets that travel through the galaxy that are not actually orbiting a star. Those are known as rogue planets. Let me show you. So this is an artist's impression of a rogue planet. For the sake of definitions, please be aware, this does not represent the exoplanet definition. This is a planet that's sailing through the cold darkness of our galaxy, but not tethered to a particular star. So we do not consider rogue planets exoplanets. It is remarkable that we can detect these objects. Not surprisingly, most of the ones we found are very high mass objects that are actually warm. They're actually giving off some heat, and some of them are very close to being what's known as a brown dwarf, which is a failed star. In case you've forgotten, gas giants and stars are very similar to each other. In fact, they're essentially the same thing in terms of composition, but gas giants are less successful, and stars are successful because they manage to do that thing which defines starhood, and that is maintain the thermonuclear fusion of hydrogen at a minimum, because there are stars that can do more than that, but at a minimum, the fusion of hydrogen. Now, rogue planets are not dwarf planets. That was the point of that little spiel. Excuse me. Where's my brain? Rogue planets are not exoplanets is what I meant to say. Wow. So exoplanets orbit other stars, and to add a little more arbitrary rules, they tend to be regarded as having less mass than 30 Jupiter masses, because that tends to be the threshold where we start to regard a gas giant not as an actual planet, but as, again, a brown dwarf, a failed star. Let me turn off that sun there. It's distracting. There you go. There, the sun's gone. Questions about that? Well, it's a good question. How would a rogue planet become free of a star system? So we don't know. I mean, there's lots of potential mechanisms. It's very unlikely they formed freely in open space like that, although we do find these type of substellar objects in star clusters. So in the case of the ones we find in star clusters that are near other stars, they seem to have formed spontaneously, but again, failed. But ones that form in a star system might be, by ratio, less just hydrogen and helium, and might have more metallicity. So, for example, an object with a rocky core or an iron core. If such an object were to become rogue, it would have formed around a star and then been flung away or ejected for some reason. And the reasons for ejection could be quite violent. Like if you had a binary pair of stars and one exploded as a supernova and it upset the gravitational influence in the solar system, perhaps the planet would go sailing away. Or what was left of it anyway, because supernova is a very violent event for a planet to experience up close. Also, gravitational interaction. So if you do have a multi-star system, let's say you have 2 or 3 suns in a system, and they have complex orbits, it's certainly plausible that they could kick a planet out of a system over millions of years as they interact with each other. As long as the planet achieves escape velocity, essentially going fast enough to leave the system, it will. But it's not just floating through space. the planet retains the inertia of its birth, and so it will be moving through the galaxy at hundreds of thousands of miles per hour. For example, if Jupiter had become a rogue planet, then Jupiter would be going about 500,000 miles per hour in its orbit around the core region of the Milky Way. So they're not floating around. They're orbiting the Milky Way's core region just like the literally billions of stars are. That's a good question. So that's someone just mentioned the trinary system. So Alpha, Beta, and Proxima Centauri are our nearest stars, a trinary system, the Alpha Centauri system, and by the way, it is host to an exoplanet. Now, on that subject, that's actually a good segue. Let me show you something. I see some chatting here. This is an artist's impression of the surface of Proxima Centauri, B. The planet that orbits the smallest red dwarf star in that system. And what you see here is cool. So we have, hold that thought, we have Proxima Centauri, which is a red dwarf star right there. And then far off in the distance, we have Alpha Centauri A and B, which are more massive, higher luminosity stars. But they're quite far from Proxima, which does orbit them in an extremely long orbit. In this case, we have 3 suns, although 2 of them are so far away that they would not contribute significant heating to the surface of this planet. And I want to repeat, this is our next door neighbor, so to speak. Proxima Centauri is the closest star to us, only 4.2 light years away. And there is a terrestrial planet, that is to say, Earth-like planet, orbiting it. That's remarkable, that the nearest star to us is orbited by an Earth-like planet. That's pretty cool. We'll talk about how we found it in a minute. We're going to talk all about how we find these things. What happens if a galaxy hits our galaxy? It happens all the time. Galaxy collisions are commonplace in the universe, and they distort each other's shape. Let me show you. These are all examples of interacting galaxies. Notice how they seem to have irregular shapes. Look at these 3 here. That's impressive. Notice how they often seem to grow tails. These tidal disruption events will cause a galaxy to change shape dramatically, but if you were living in that galaxy, you would just go along for the ride and experience no inconvenience for it. Essentially, when you live in a star system, it's like a little island, and you orbit the star, and again, the star goes along for the ride, and you go along for its ride. So galaxy collisions, not bad, not violent, not dangerous. However, they can be positive. So even though they're not destructive, galaxy collisions tend to result in rapid star formation because you've shaken up the system. You have a lot of gas and dust which starts to pile up and then will collapse under gravitational attraction. That was kind of a tangent, although worth talking about. Okay. So, I'm going to give you a little history lesson. I mentioned something about the 1990s earlier. This chart is pretty good, and this was just updated a few months ago, so as you can see, it has 2020 data on it. What you're seeing here is a chart of the number of exoplanets we've discovered, and it details the methods that we used to find them. And we're going to go through all of these methods one by one. You can clearly see that the transit method, whatever that is the most successful. Notice all the green. We'll talk about that in a minute. We're going to go in order. But notice that the first thing on the list, direct imaging, doesn't seem to be very successful. We haven't found a lot of exoplanets via direct imaging. Now, you don't need to be an astronomer to figure out what direct imaging means. That literally means exoplanets that we've been able to take pictures of. So let me show you I think I have a picture of that. Let's see. Hold that thought, guys. Oh yeah, right here. This is a rare example of a directly imaged exoplanet, and this is Pictoris b, and then the star Beta Pictoris. So it's Beta Pictoris b. This is a nearby star system, and using infrared light, we were able to find this planet and actually take a picture of it. I want to repeat, that is extremely unusual. It is very rare that we can directly image a planet, and the reason is simple. Planets don't really give off any light, and they're right next to something that gives off tremendous light. The telescope that was used to take this picture has a special occlusion disk coaxial to its aperture, which blocks the glare from the star. And you can see it there in the middle. It's kind of a dark circle. And it blocks it enough that you can actually image objects directly adjacent to it. If you attempted to do this at home, if you tried to take a picture of Beta Pictoris b, you would not be able to find it because it would be completely lost in the glare of Beta Pictoris. So yeah, direct imaging, very, very difficult, and not the best candidate process. But it is exciting when we can do it. Any questions about that? Hold that thought. Let me go back to my chart. Glowing planet, that's funny. Yeah, just so you know, planets will glow in infrared light if they're very hot. So for example, a type of exoplanet known as a hot Jupiter, and we're going to talk about those, might glow warmly enough, so to speak, in infrared to be seen with infrared telescopes, but not with visual, because again, it's blown out by the glare of its parent star. Okay, so direct imaging is exactly what it sounds like. You're literally taking a picture of a planet, and as you can see from the chart, not a very successful method. Now, the next method of finding exoplanets on the chart. Microlensing. Now, I'm going to show you an impressive picture. Some of you might know what this is. This extraordinary structure is known as an Einstein ring, and it's not really a ring. What you're seeing is the light of a very distant galaxy, this pink ring, being distorted and bent into this circular shape by the extremely intense gravity of this foreground elliptical galaxy cluster. So you have a cluster of elliptical galaxies here in the foreground, and their enormous gravity is bending light so much that a galaxy behind them, which would have been obscured by them, is actually seen because the light is being bent around them. This is gravitational lensing, not microlensing. This is a remarkable phenomenon that was predicted by Albert Einstein, and that's why we named it after him, Einstein's ring in this case. Here's another one. Again, another Einstein ring. This one's impressive because it almost completes a circle around the, again, foreground elliptical galaxy. So we have a massive foreground galaxy, and again, a galaxy that was behind it being distorted into a ring. Now, with computers, it's actually possible, believe it or not, to reconstruct the image of the background galaxy and actually get a pretty decent picture of it. So yeah, that's one of those things that modern astronomy can do thanks to computer science. Now, again, this is not gravitational microlensing. This is absolutely large scale. Let's talk about microlensing. This is a technique which can be used to find planets. So, here's how it works. We have a star being observed 3 times, and we have a planet that is moving between us and the star. So it's moving downward. See the arrows there? Now, when the planet passes directly between us and the star, it essentially bends the star's light in such a way that the star appears artificially enlarged. So we've essentially, if you will, magnified the star with a gravitational lens. Now, the reason we call this microlensing is because, not surprisingly, this phenomenon is extraordinarily minor, it's slight, it's subtle. So you have to use very advanced telescopes. If you want to observe microlensing from Earth's surface, you need to use what's known as adaptive optics technology, often, not always, to compensate for Earth's atmosphere. Although sometimes that microlensing event can actually manifest as an apparent increase in brightness. So there are actually systems for detecting microlensed stars that are not huge. We're not talking about gigantic observatory telescopes. It is possible to construct an array of small telescopes to detect this phenomenon. And I'm going to show you some examples of that in a few minutes. So this is gravitational microlensing, and this is another method of finding exoplanets. Any questions about that? I feel like there's going to be a question about this. I'm going to wait a second. I'm watching the chat. Oh, I missed the question, and it's not off topic. What do you mean by failed? Most objects in the universe fail. Stars try to form, and they will begin their lives if they begin thermonuclear fusion. If a star does not gain enough mass to generate enough gravity, pressure, and temperature to undergo thermonuclear fusion of hydrogen, then that star is considered a failed star. By the way, in this case, in this context, you would probably need a living star to get this done because the luminosity of a living star will be intense enough to measure in an experiment like this. A failed star would be very difficult or impossible to microlens because it doesn't give off much or any light. Yeah. Questions about that? Is the lens a planet or a galaxy? So I just showed you two examples. Let's make sure we understand that. This is gravitational lensing, which is an enormous, large scale phenomenon. We're talking about, in this case, a set of galaxies that are literally billions of light years away. And we're talking about so much mass that the effect is not subtle. I mean, look at this. We've bent the light of a galaxy into a ring. Again, that's because we're talking about, in this case, the combined mass of multiple foreground galaxies that literally contain hundreds of billions of solar masses, maybe even trillions, depending on the size of the galaxy. So that's a gargantuan amount of mass. Same with this picture. In the case of a planet, because it has very little gravity, the effect is, of course, minor, and so that's why we call it micro-lensing and not just lensing. And for this to work, not only do you need the planet to be heavy enough to bend the starlight enough to see it, but you have to have the extremely unlikely coincidence of the planet crossing our field of view perfectly, so that it eclipses, so to speak, or in this case, it transits the star. However, this method is not what is known as transit photometry, which we're going to talk about next. Questions? How to do the computations? Math. Lots of math with very smart people and expensive supercomputers. Oh yes, so I see what you're asking. You're asking for the actual formula. I don't know it off the top of my head, although it's not that complicated. The problem is not the formula. It's having enough dynamic range to be able to determine the different levels of brightness, or size, if you will, in this case. So that's more of an instrumentation challenge than a mathematical challenge. That's a good question. Okay, I'm going to get off microlensing, get back to my chart here. Ooh, now we're on to transit. And as you already observed, the transit method has been by far the most successful. I don't know if you noticed, but in the top of this chart, it actually has the number of planets found in a given year. So look at this. In the year 2014, we found 853, or rather, let me rephrase that. We confirmed the existence of 853 exoplanets. In 2016, we confirmed 1,471. In a single year, confirmed the existence of 1,500 alien worlds, planets that are orbiting other stars. Before I continue, I need to point out something. When I was a kid looking up at the stars and pondering the concept of alien planets, what struck me as profound was the fact that these are places. When you look up at those stars in the sky, they're not little dots. They're not points of light as our ancestors used to think. Those stars are huge bodies orbited by other bodies, which you could, like I said, visit or stand on. I showed you that artist impression of Proxima Centauri b. This is a world that one could perhaps explore one day. I'm not going to keep my hopes up for that. These are great distances. Even Proxima Centauri, our nearest star, 4.2 light years away. That's a gargantuan distance for humans. The Voyager spacecraft, the fastest thing ever made, Voyager 1, will take 18,000 years to go 1 light year, and it ain't going in that direction anyway. So it is, even a quote, nearby star system is very far away within the context of our current space exploration technology. But again, these are places, locales, and perhaps some creatures are there observing sunsets like that. I doubt it, but it's a neat thing to think about. But think about the billions of sunsets and sunrises that happen every day that no one gets to observe because they happen on empty worlds. That's deep. So anyway, the transit method, by far the most successful. It's also probably the easiest to explain. I'd say second easiest, because direct imaging is pretty simple. You take a picture of a thing. But it's easy to explain the process. So here's a drawing of the mechanism in a nutshell. Simply put, transit photometry is the measurement of the brightness of a star changing because a planet has transited it. That planet has crossed the star. And as a result, the star's light has momentarily dropped. Now, this is not an eclipse. As you can see, the planet is too small to eclipse the star. What we're seeing instead is a very subtle dimming. Now, it's easy to explain this mechanism, although in practice, it's very difficult to do because the difference between this point in the light curve and this point is very small. I've often heard people use the analogy of like trying to measure the brightness of a light bulb with a fly crawling across it or not. But that would actually still be a lot easier than what we're talking about here. So it requires you to use an instrument with extremely high dynamic range that can distinguish this value from this one. So we built this thing. Here's one such instrument. This is the Kepler Space Telescope. May she rest in peace. It's essentially no longer operational. This extraordinary instrument, for years in recent history, studied many stars and watched for that telltale drop in brightness. Now, I want to make sure you guys understand that. Oh, someone asked me a question, are these transits rare? That's just where I was going with this. So, when Kepler was designed and built, the mission planners were highly pessimistic about its chances of success. I want to see if you can figure out why. Someone tell me. What is wrong with this method? What is extremely unlikely about this method in terms of success? Why should this method not work very well? What do you guys think? I want to see if you can figure it out. I'm gonna wait. I want to see some answers. Why is this method so unlikely to be successful? I'll give you a hint. Something unlikely needs to be true for it to work. That's an interesting question. Is there not an ambiguity whether you're observing increase in brightness due to microlensing or decrease due to transit? Well, and we studied the light to figure that out. And there's also some Doppler shifting at work too, which we'll talk about in a minute. Same plane, very good. So someone points out that for this method to work, yes, so, oh good, you're all getting it, very good. Exactly, very good. The ecliptic plane, the plane of that star system, has to perfectly agree with our line of sight, or else this ain't gonna work. And so, as a result, mission planners were very pessimistic because they thought, what are the odds of that being true? They thought, oh, we might find a few dozen. Maybe we'll find a few hundred planets. But we did much better than that. Now, I want to show you something cool. I'm going to put the sky on the screen here. Here's the sky. This is the sky from Goldendale. Let's pause time. Let's go back to now. I'm going to zoom in a bit here. And I'm going to turn on all of the star systems that are currently known to host exoplanets. Watch this. Okay, see all those green dots that just appeared? Those are all the star systems that are known to host exoplanets. It seems like a pretty good haul. It seems like we found quite a few, but watch this. I'm going to go over here to the summertime sky. This is the summer sky. And I'm going to do the same thing. I'm going to turn on all the exoplanetary system. Watch. What the heck is that? Going to get a little closer here. Oh, look, more things are happening. What is going on? What you're observing, my friends, is the Kepler survey. And every one of these exoplanetary systems was confirmed by the Kepler Space Telescope and sometimes follow-up observations. But Kepler made the initial discoveries. Every single one of these green dots with all words next to it is a system that was confirmed to contain exoplanets, discovered by the Kepler Space Telescope, which stared at exactly one spot in the sky, it's part of the constellation Cygnus, for 5 years, using the transit method. Now, why did it have to stare at one spot for 5 years? Why didn't it just explore the entire sky? What do you think? Why didn't the Kepler Space Telescope study the entire sky? Why did it stare at one spot for 5 years? What do you think? Any thoughts about that? What do you think? Why did it stare at one spot for 5 years? Good. Transits are rare. What if you saw one and then it looked somewhere else and missed the next one? Well, now we know nothing about that planet. For example, we might assume it was a fluke. If a star's brightness dipped suddenly, it might have been a number of things. It could have the star actually dipping in brightness briefly. It could be some instrumentation error. It could be sensor noise. But if you see that light dip occur again and again, Now you know something's going on. It's a real event, a real result. But you got to stare at one spot in order to successfully detect those type of events, don't you? Now, how many of you noticed that there seems to be a checkerboard arrangement? Notice how it seems to be arranged in a series of squares? You might love this. The reason for that is quite simple. This is a photograph of the sensor of the Kepler Space Telescope. As you can see, it's a series of sensors, and they work together as one single large unit. And this is the array that studied that one spot in the sky for 5 years. Notice there's a curvature to it. That's to correct for geometric aberrations created by the lenses and mirrors in the instrument. So Kepler Space Telescope stared at one spot for 5 years, and it found many planets. Check it out. Let me turn that brightness off. So I'm going to turn off my head here. By the numbers, Kepler's was up there for almost 10 years. It used only 3.2 gallons of fuel. That's impressive. It observed the light of over 500,000 stars. It collected 678 gigabytes of data, which was, as you can see, beamed to Earth and collected by the Deep Space Network antenna array. Look at this. It confirmed 2,662 planets. Almost 3,000 scientific papers have been published thanks to its data. And this is, I don't know why they found this worthwhile to mention, but it did actually execute 732,000 commands, which does speak to the reliability of the spacecraft, the fact that it was able to respond successfully to so many commands without breaking. And then look at this. As a bonus, 61 supernovae documented. And notice how it says from the earliest stages of the explosion. The reason this is interesting is because since Kepler has an extraordinary dynamic range, being able to detect very slight differences between wave peaks, it's well equipped to find supernova explosions in their first moments when the star just begins to increase in brightness. So yeah, that's something that was kind of a bonus function of Kepler, its ability to do that. As you can see, 94 million miles away, it orbits the sun essentially in the same distance that Earth does, which is not surprising because, again, it's inheriting Earth's inertia. It would be expensive and difficult and fuel-intensive to send it off into some other orbit. Of course, we do that with other space telescopes, though, so it's not like it's out of the question. Now, before I go back to the stuff I was talking about, are there any questions about this graphic or the interesting factoids that NASA has provided us? Gather enough sample. What does that mean? Let's see. Okay, so the transit method, wildly successful. Let's go back to our chart here. Because it is a big deal, because the transit method is so successful, would anyone like to ask a question about the transit method before I move on to the other methods? Kepler's not the only space telescope or telescope on Earth additionally, that has successfully employed this method, but it's clearly the most famous. It's the rock star of the transit method. It will eventually be replaced. Someone points out that 700 gigabytes is not that much data. Well, consider what the data is. We're talking about luminosity values, so it's monochromatic data. We're not talking about spectral signatures, although there is some light spectra data. We're talking about essentially the luminous flux of a very tiny point of light, and that type of data can be easily compressed. So yeah, I mean, and by the way, you don't want a space telescope to generate too much data, or let's say be inefficient with data, because then you have a serious problem with downlink. You have to get the data out of the space telescope, and because it's literally millions of miles away, it experiences very low bandwidth. And so if the telescope was generating gigantic amounts of data, then we would be waiting gigantic amounts of time to download its readings. That's a common problem with spacecraft, is getting you can store data, but it only has so much storage on board, but then you got to wait to get that data because of the extremely weak signal and the low bandwidth. Good question. What happened to Kepler? So once Kepler's helium, it had liquid helium on board, ran out, it was no longer able to supercool its sensor enough to achieve the necessary dynamic range to distinguish between the brightness levels, and so it became essentially useless at that point. It also had some issues with its orientation systems. And you may have heard, it was kind of clever, after Kepler essentially lost the ability to point in the direction that NASA wanted it to point, they did something very clever. They call it the K2 mission, where they repurposed the Space Telescope's navigation system to rely on solar wind to act as a sort of thrust. So they allowed the Space Telescope to precess in position by reacting to solar wind pressure. Now you're thinking, well, solar wind is very, very weak, and it wouldn't provide very much pressure. That's right. And so it would take literally weeks or months for it to change position thanks to solar wind. But isn't that clever? So you can imagine this big solar panel acting like a sail almost. Aren't we clever? I love stories like that. I love stories about a machine breaking and people are like, well, we can't go fix it, so let's make the best of the situation. That's what happens when you hire very smart people and give them access to impressive resources. Yeah. Questions? Can microlensing be seen in our solar system? That's an interesting question. You could argue that the microlensing of starlight by the sun's gravity is an example. That's, again, how we proved relativity. It's how we proved Einstein right, way back in the first quarter of the 20th century. So yeah, I guess you could say that, sure. Okay. Transit photometry, as you can see, has been highly successful. However, as we already discussed, it's not perfect. In fact, it leaves out a lot because, again, it relies on that perfect chance alignment of the ecliptic plane of a foreign or an alien star system agreeing with our line of sight. Now, that being said, before I continue, I need to point out something extraordinary about this data. What does it tell you about exoplanets in the universe? If a method that is known to be flawed works very well. I want to answer for that. Someone give me an answer. Why is that such a big deal? That a known bad method, a flawed method, a troubled method, an unlikely to succeed method is very successful. What does that tell us about planets in the universe, guys? I want to hear the answer. Come on. What do you think? There are a lot. Very good. And that was the true mind-blowing revelation brought to us by the Kepler Space Telescope. We employed this flawed method of detection and were wildly successful, and suddenly we realized, indeed, science fiction was right. The universe is full of planets. Having planets is something that stars do. Extraordinary, yeah. And now we know a few more things. I'm going to jump ahead a little bit. Not only do we now have the ability to find planets, we can also learn things about them. And one of the things we've discovered is Earth-like planets are far more common than we expected. It turns out that stars like the sun, sun-like stars, which are considered intermediate mass stars, that 1 in 5 of them will have a terrestrial planet orbiting it. Isn't that a big deal? Again, science fiction got it right. The universe is not only full of planets, it's full of Earth-like planets. Wow. But when I say Earth-like, that doesn't mean it's a lovely paradise with alien jungles and strange creatures. It could be a horrifying nightmare world like Venus, or a different kind of nightmare world like Mars, or some third, even more terrifying form of nightmare world that we can't even imagine. Maybe it has acid oceans, for example. You can't assume just because a planet has the similar size and mass of the Earth, or similar composition, or similar distance from its parent star, that it's going to be a nice place to live. We need to temper our enthusiasm a bit when it comes to finding these exoplanets. Just because they exist doesn't mean that they're lovely places to be. Oh, one question. Now, this is a very interesting point. This is actually a very big deal. Someone asks, how many of those planets are in the Goldilocks zone? Most of them. Now, before you get shocked and say, wow, not only are there tons of planets, but tons of them are in the Goldilocks zone, we know that it's an artifact of detection bias because the methods that we employ to find planets rely on the planets being relatively close to the parent star. It is very difficult to find planets that are orbiting far from their star because it makes all of the challenges essentially more challenging. So unfortunately, we have a confirmation bias right now towards Goldilocks planets. That doesn't mean that most of the planets in the universe are Goldilocks, and we're aware of that. So it's important to understand that a non-result is also a result in science. And when we build theoretical models, we have to take that into account. We have to make some sometimes very generous assumptions, sometimes very well-informed assumptions. It depends on how much we know. Because this is a new science, we're still making a lot of guesses. The good news is it's evolving very rapidly because now that we know that there's planets everywhere, everyone wants to get in on this. And so there's lots of new missions being planned and lots of new data being collected. Hold that thought because by the end of this, I'm going to talk about some of the next steps. Yeah, good question. Someone mentioned the Drake equation. I don't like talking about the Drake equation because I think it's full of wishful thinking and all sorts of leaps of logic. But if those of you who are not aware, the Drake equation attempts to guesstimate how many advanced civilizations might live in a galaxy. And if you plug in all the numbers, including these new numbers, you end up discovering that the Milky Way must be full of advanced alien civilizations. I take the conclusion with a grain of salt. There's a lot of, again, assumptions being made, a lot of wishful thinking, a lot of fantasy being presented as opinion. Anyway, I'm not against the Drake equation. I just don't take it as seriously as some people do. Although, and it does segue into a whole other topic I'm not going to talk about tonight. It does, of course, force us to ask that question. If the universe is absolutely full of worlds, then where is everybody? Where are all the aliens? We might talk about it at the end, but probably not. I don't have time. We're going to do a whole show about that someday. By the way, that's the Fermi paradox, the great question of where is everybody? And that question keeps getting worse and worse. It keeps getting more and more compelling as we discover, oh yeah, the universe is full of planets. Okay, radial velocity method is the next topic. Now this method is nice because it does not require alignment. What we're talking about in the case of radial velocity is the subtle wobble that is induced on a star by planets that are orbiting it and tugging on it. Again, the good news is you don't need a perfect alignment with the ecliptic plane of the system and your line of sight for this to work. Let me show you. This is a highly, highly, highly exaggerated animation depicting the wobble. So we see the small body, the planet, tugging on the big body, the star, and inducing this wobble. Now, if I had to relate this to our own solar system, there is a relationship like this in the case of Jupiter and the Sun. You guys might be aware of this. It's very interesting. The red X or cross in the middle is the barycenter of the system. Jupiter is the only object that orbits the Sun in our own solar system that orbits a barycenter that is outside of the Sun. The Sun wobbles so much because of Jupiter's influence that Jupiter actually orbits a point above the Sun's surface. Not very far above, but it's outside of the Sun, which is quite neat. Nothing else in our solar system is so heavy to induce such a significant wobble. So, interesting topic. Now, the motion of the star. It's going to bring the star closer to us, or farther from us, or closer to us, or farther from us. And this induces the famous Doppler shift phenomenon. So you may have seen this animation I made a few weeks ago. If you have an object emitting electromagnetic waves, and you're stationary in relation to the object, essentially you share the same inertial reference frame, then it doesn't matter where you are. If you're over here, or if you're over here, or if you're over here, you're going to observe the same frequency of radiation. But if there's relative motion between you and the emitting object, then we're going to see Doppler shifting. So let me show you. So if you're standing over here, so to speak, you're going to experience a higher frequency of waves, and if you're standing over here, you're going to experience a lower frequency of waves. Now, before I show you, does anyone know which side of the star, let's say it's a star, which side is blue shifted and which side is red shifted? Let's see if you guys know. I'm going to wait. Tell me. Right or left? Which is the blue shift and which is the red shifted side? Someone tell me. I'm watching the chat. Blue shift is on the right. Very good. And so the red shift is on the left. And the reason is simple. Blue is higher energy, higher frequency, shorter wavelength. And red is lower energy, lower frequency, longer wavelength. And when an object is moving away from you, per se, it stretches the waves of light, and you get red shift. If something's moving towards you, it compresses the waves of light, and you get blue shift. So here we go. There you go. Now, this animation, of course, dramatically exaggerates the effect for clarity. If you were to actually study the light of a given star using off-the-shelf equipment, you would see none of this. You would not be able to detect any appreciable blue or red shift. But using very advanced telescopes with extremely high resolution spectrographs with extremely high dynamic range, it is possible to measure blue shift and red shift of the star's light and it allows you to reveal the wobble induced by a star. Now, someone asks a deep question that Isaac Newton grappled with. How do you decipher the wobble caused by multiple orbiting bodies? That's known as the many-body problem. Ironically, it is not a problem in the context of exoplanet research because multiple bodies inducing different levels of wobble interact with each other, and that allows you to find them. So essentially, if you see shifting of the wobble that is out of time with another shift, you know that there's some other actor at play and there's something else going on. So we actually use that problem to find some exoplanets. And by the way, that's one of the mechanisms listed in that chart I showed you. We're going to get to that in a second. So yeah, the many-body problem, although it vexes us still to this day, it is, of course, the playground of supercomputers and computer scientists who love to find better ways to crunch those huge numbers. But the many-body problem also creates an opportunity to find more bodies because you can tell that they're doing something. They're perturbing the system in some way. That was interesting. Right. No, that was wrong. So, all right. Questions about that? That was a good question. All right, back to the chart. And look at that, perfect timing. That was an unintentional joke. The final metric here is timing. Timing entails exactly what I just described, where you have multiple bodies affecting each other and causing shifts in time so that a seemingly regular interval event like a single planet orbit is being disrupted in some way, or that planet is being disrupted. Now, if you look on the chart, you will see that we've been discovering exoplanets all the way back into 1988, although that 88 discovery is a retroactive discovery where we found that later in the data. The date that I really want to talk about is here, 1992. This was the first confirmed exoplanetary discovery, and notice that in 1 year, 1992, we found 3 exoplanets. And they were found using the timing method. But this is bizarre. I mentioned earlier that the first one we found was in a very unusual circumstance, and that is because this is a pulsar system. So, let me get my head out of the way because this is pretty artwork. Actually, I'll put it over there. There you go, that's fine. So, this is, of course, an artist's impression, a drawing. The PSR B1257 plus 12 pulsar system, which is 2,300 light years away in Virgo. Before I continue, think about that. The first ever discovery of an exoplanet occurred around a dead star that was 2,300 light years away, so not nearby. That's very strange. So, in a nutshell, you guys probably know from previous shows that pulsars are rapidly spinning neutron stars that are host to immensely powerful electromagnetic fields. These enormously powerful and spinning electromagnetic fields excite particles in the system enough that they emit radio waves. If the beam of radio waves washes over our perspective here on Earth, if it washes over our star system, then we detect not a continuous signal, but a pulsation. What we discovered is there was some Doppler shift in the pulsation induced by the motion of planets. And by comparing the pulsation to the apparent or theoretical orbit of the unseen planet, we discovered there were problems, there were errors, there were other motions being induced, which led us to discover that not only was there a planet in this system, there are 3 planets. So we found 3 exoplanets orbiting a dead pulsar. Now, the reason I say dead, neutron stars are the result of the death of high-mass stars. What is shocking about this system is you can say with some confidence that these 3 worlds are ruined, that they are barren wastelands because they were present for a Type 2 supernova. The temperatures they would have experienced would easily have melted their surfaces to glass. They're probably smooth and fractured. These poor planets almost certainly have been wrecked by witnessing the death of their parent star. So yeah, what a depressing system. And as a result, these planets have nicknames that are all kind of mentioned undead creatures like that, and they call this the Lich star, which is like a ghost or something. So yeah, that's an interesting system. So look it up if you're interested. It's, again, I always forget the name. PSR B1257. If you search for that, you should find, this is the most famous object with those first letters and numbers. You should find this system. It's quite interesting. So think about that. The first exoplanet system ever confirmed was way back in '92, and it was confirmed via this wild method detecting shifts in the radio emissions of a pulsar. Questions about that? Questions about the methods that we use so far? Any questions at all? I don't see a lot of movement in the chat. Okay, now, the other irony, and I already mentioned it, but I think it's worth repeating. The irony of this discovery is that this system is far away, 2,300 light years. Not surprisingly, there is an extreme proximity bias when it comes to exoplanet research. Get my hat out of the way. Actually, I'll just get out of here. Oops, wrong button. So this chart illustrates exoplanet numbers of discoveries over distance. And as you can clearly see, nearby systems, well, look at that. We found a lot more planets. Not surprising, since the closer these things are, the easier they are to study, and the more pronounced the phenomena we're discussing are. Now, in case you need some translation here, the leftmost column here, the vertical column, is how many planets we found. And this column, this axis, wow, this line illustrates distance. Now, in case you don't remember, parsecs are 3.26 light years, so that means 1,000 parsecs would be 3,260 light years, which is pretty far. As you can see, we get farther and farther out, and we find less and less things. Again, not surprising, but it is a little bit depressing because, and this is similar to so many things in astronomy, we tend to do a lot better with objects that are nearby because they're easier to study. Any questions about that? Now, this also leads to a more fantastical question, because you might assume, if you know anything about distances, that this chart seems to imply that 100% of exoplanet discoveries have taken place in the Milky Way galaxy. That is mostly true, mostly. However, there is a short list, a very small handful of exoplanets that we have discovered in other galaxies, believe it or not. Hard to confirm, by the way. And the reason it was possible is because, similar to the story of the PSR B1257 system, these were planets orbiting extreme objects like pulsars. And so their radio waves are being disrupted. So yes, there is a very short list of exoplanets that we have found in literally other galaxies, but not surprisingly, they are extremely, extremely difficult to detect. Questions about all that? I'm going to put this picture back on the screen because I like it. It's pretty exciting. Okay. Any perturbations point to additional solar planets? I'm not sure I understand the question. What do you mean by solar planets? Planets orbiting sun-like stars? And the answer is, again, I'll repeat, there's a lot of them. It turns out that sun-like stars apparently often have Earth-like planets orbiting, 1 in 5, in fact. Wow, that's quite a large number. Now let's talk about kinds of, we're getting close to the end. Let's talk about types of exoplanets. You're going to like this. Okay, the image on the left is the Earth, and I'm just going to put my head back because I think you know what Earth looks like. The planet on the right is Kepler 452b. That is a super Earth, and that is a term. That is a type of exoplanet. A super Earth is a terrestrial planet, so a rocky, metal-rich planet that is bigger and or more massive than planet Earth. There's lots of super Earths out there. We don't know if that's good or bad. We don't know if it's negative or positive, although this might blow your mind. This might intrigue you. This might inspire your imagination a little bit. It has been estimated that if you were to attempt to live on many of the super Earths that we are discovering, rocketry would be impossible. You would not be able to leave many of the super Earths using rockets because the gravity is simply too strong. You couldn't build a rocket using the concepts that we use to build rockets on Earth that would actually successfully get you out of the planet's, even just the troposphere, the lower part of the atmosphere for the most part. So yeah, in a way, lucky you, we don't live on a super Earth, because if we did, we might be stuck here. We're still pretty much stuck here. It's pretty hard to get to space, but it would be even more difficult if you lived on a super Earth. Any questions about that? Of course, if you did evolve on a super Earth, you'd probably have big muscles, wouldn't you? You'd probably be very strong. All the animals would be very beefy, and they'd have big, thick legs probably because they had to keep themselves up against the weight. Or maybe you wouldn't have tall animals at all. Maybe everything would be a low-profile animal like snakes and worms and things like that. Hard to say. It's fun to think about. So that's a type of exoplanet. Super Earths. Questions about that before I move on to the next one? Okay, here's another one. Here's a fun one. Hot Jupiters. Let me flip that. There you go, that's better. Now it's not my way. A hot Jupiter is the term we use for a gas giant that is too close to its parent star. Now, I mentioned something earlier. We have an unfortunate detection bias towards planets which orbit close to their stars. So it doesn't necessarily imply that hot Jupiters are common, although we do keep finding lots of them. Hot Jupiters are interesting because these planets will lose a significant amount of mass to solar wind or astral wind ablation. The radiation output of the star will strip these planets of their outer layers. A hot Jupiter would be a very hot and violent place. And perhaps it could even be completely stripped. There is a type of hypothetical object known as a Chthonian planet, where it's a gas giant that's been completely stripped of all of its gas, leaving only the core, which would be comprised of heavy elements like iron and rock and things like that. We don't know if they exist or not. It's an interesting hypothesis, though. Now that we know that population 2 stars can host planets, it may be that there are star systems old enough that a hot Jupiter could have been utterly stripped. I want to point out, like I said earlier, we now know that there are population 2 star systems, planetary systems, which means they're around 10 or 11 billion years old. That's more than twice the age of our solar system. Yeah. In that amount of time, maybe you'd have more time to wreck a gas giant with radiation. Yeah. How do you tell the difference between a hot Jupiter and a super Earth? That's a very good question. Partly, believe it or not, there's actually some pretty common sense answers to that question. So, for example, a gas giant is significantly larger, and because of that, it will actually create, for example, a longer duration transit where we can see the beginning, the middle, and the end of the disk of the world entering the disk of the star from our vantage point. The longer that takes, essentially, the bigger the planet. We can also measure the mass of these bodies if they're perturbed by or perturbing other bodies. I mentioned the many body problem, and figure out, oh, this is too massive to be a terrestrial planet. It has to be a gas giant, for example. And then sometimes we can actually, believe it or not, measure the spectra of the planet's atmosphere, and that again informs us of what it is. If it's all hydrogen and helium, then obviously it's a gas giant. Yeah. Oh, by the way, I don't have a picture of it, although I wish I did. 'Cause they're always drawings and paintings; they're not real. But if you were in such a system, the planet would probably not look so lonely. It would probably have an enormous tail of material streaming away from it. It would be like a giant super comet. Except that it wouldn't be streaming dust, it would be streaming plasma, hydrogen, and helium, yeah. Interesting. Questions about that? Okay, now here's a fun one. This is kind of a rare one. You're going to like this. A super Saturn. Let me get my head out of the way. A super Saturn is, as its name implies, a planet with an unusually advanced or very large or very massive ring system. And super Saturns are fun because they do some weird things that lead to all kinds of ridiculous conjecture. You may have heard of a Tabby's star, and there's a few other examples. These are stars that behave strangely. Their light curves seem to shift in a chaotic, complex manner, which may indicate some sort of structure is filtering their light. You may have heard of the alien megastructure star. Sometimes when we find stars that have weird variability in their light output, we think there's some colossal extraterrestrial object, like, for example, a Dyson swarm or a Dyson sphere orbiting the star. The aliens have constructed a giant structure. It's most likely that those systems are home to super Saturns. And we have found evidence of super Saturns where we can confirm that that's what's going on, based on the spectra of the starlight being altered by the ice and dust of the ring system. Yeah, that's a fun topic. So yeah, super Earths, hot Jupiters, super Saturns. Questions about that? And then, of course, we have regular planets, Earth-like planets, and terrestrial planets or gas giants. Yeah. So we don't have cute nicknames for every kind of planet because we don't need them. Because some of the analogs, some analogs exist to planets in our own solar system that aren't that very different. Now, briefly, I forgot to use this slide. I wanted to show it to you really quick. Someone asked about failed stars. So this is a size, scale, accurate representation of different types of stars and planets. We have the Earth here for scale, and of course, good old Jupiter. Now, you guys probably know without any doubt that Earth and Jupiter are considered planets. But then look at a brown dwarf. A brown dwarf is a failed star. Brown dwarfs could have become stars, but they never gained enough mass. And in case you're wondering, for a planet like Jupiter to become massive enough to transform into a low mass or red dwarf, by the way, that's what this yellow one is. I know it looks yellow, but this would be a red dwarf. Jupiter would have to gain 75 to 80 times more mass. So a brown dwarf will have less than that, like for example, 30 Jupiter masses, or 50 or 60. So yeah, we have planets, Earth and Jupiter, failed star, brown dwarf, successful low mass star, red dwarf, and then in the background there, an intermediate mass star, which by the way is the sun. You guys have often learned in school that the sun is small, and it is as stars go, but it is bigger than the most common stars in the universe, which are low mass stars. Yeah, and those are red dwarfs. You might be astonished to learn that about 70% of all stars are red dwarfs. The most common star in the universe. And by the way, how many can you see with the naked eye? Does anyone here know? How many red dwarfs can you see with the naked eye? Anyone want to answer that question? Someone asked, do exoplanets collide? Oh, definitely. I mean, things that collide in our own solar system. 0, that's right, very good, none. You cannot see a single red dwarf, even though they are the most common stars in the universe. This gives you some insight into how small and how dim they are. Some of them are close. There's a certain red dwarf system that's only 7 light years away. There's another one that's only 12 light years away. There are red dwarfs that are, as stars go, are right on our doorstep, and yet you cannot see them because they're so dim. By the way, your view of the sky from Earth is biased towards extraordinarily close, luminous, or huge stars. So you are not seeing even one member of the most common type. We tend to be biased towards extraordinary objects because we are so bad at astronomy. We're so bad at observing the universe. Yeah. Questions about that? All right. So in the interest of wrapping it up, some of you have heard me talk about this too much, but I still think it's worthy of discussion, and that is the remarkable TRAPPIST-1 system. TRAPPIST-1, hey, so someone just asked a question that is actually how I intend to end the show, so yeah, hold that thought. Someone asked, how do we measure their atmospheres? Could all gas giants form a star? That's a good question. The answer is no. It's based on how much material they have access to. When a star system turns on, when a star is born, radiation pressure actually pushes material away. So any loose monoatomic hydrogen that could have been eaten by the gas giants will be ejected by the radiation of the young star. So once a star system is born, so to speak, when the star is shining, then the gas giant planets in the system will essentially be robbed of any further food, any further fuel to gain more mass by the radiation of the system, star, yeah. All right, so famous system, always worth talking about. TRAPPIST-1 is an ultra-low mass red dwarf star. This is a star. Notice it's only slightly larger than the planet Jupiter. It's always important to remember that size and mass are very different things, especially in space science. Some of the heaviest objects in the universe are small, like obviously black holes and neutron stars, things like that. So TRAPPIST-1 may be the same size as Jupiter, but it's about 80 times more massive. Now you might, if you were paying attention, that means that TRAPPIST-1 is at the absolute bottom of the barrel. It's at the minimum threshold of starhood. It's just barely able to maintain hydrogen fusion because it's just barely heavy enough to create just enough gravity, or excuse me, just enough pressure to create just enough heat to do it. Now, TRAPPIST-1 was discovered a few years ago, and when NASA announced it, they really, really hyped it up. They made it out to this huge deal. And they were right to do so because this system is extraordinary. Let me show you what I mean. So you have 7 Earth-like planets that all orbit within the Goldilocks zone or excuse me, 3 of them are in the Goldilocks zone, D, E, and F. All 7 Earth-like planets orbit within a space that is smaller than the planet Mercury's orbit in our own solar system. So it's like a miniature star system. Look at that. And the reason I like to end the show when I talk about TRAPPIST-1 is we've been able to employ multiple methods to study it. It was discovered with the transit photometry method, but then we were able to detect the number of planets in the system by the way they perturb each other, which is that timing method that we talked about. Any questions about that? Look at the size and the speed of the orbit. So look, the closest planet in TRAPPIST-1 is only 1.5 day year. So it takes it only 1.5 days to go around the star. The longest year in the system is 20 days. Think about that. And now planets TRAPPIST 1, D, E, and F, those are the ones that exist in the Goldilocks zone. We didn't really talk about the Goldilocks zone tonight, but in a nutshell, it's the zone where you might expect to find liquid water. It's not too hot, not too cold. But I want to remind you, that doesn't mean that these are nice places to live. These are drawings. There may not be any water on these bodies, or lush alien jungles, or other fantastical things. They may be horrifying places like Venus and Mars. Who asked, can red dwarfs fuse helium? So at the end of a red dwarf's life, some can fuse helium and some cannot. The ones that cannot, and by the way, red dwarf TRAPPIST 1 is one of them, it will actually collapse into a helium white dwarf. These are stellar remnants that don't really exist yet because low-mass stars like TRAPPIST 1 have not started to die yet because they have extraordinarily long life cycles. This might blow your mind. Our sun will live about 10 billion years. TRAPPIST 1 could live hundreds of billions of years because it uses its fuel very slowly and it's internally fully convective, so it does not waste its fuel. When the sun dies, it will have wasted most of its hydrogen. People misunderstand. When they talk about a star running out of fuel, they don't actually mean that it's exhausted every atom of hydrogen inside of it. It's exhausted the hydrogen that it has access to, the hydrogen that can be close enough to the energy centers that can fuse it. In the case of our sun, it will die having wasted almost all of its fuel. TRAPPIST 1, not so much. TRAPPIST 1 will use almost all of its fuel, and that gives it a mind-bogglingly long life cycle. Stars like TRAPPIST 1 have not started to die yet. I think that's pretty profound, actually. This might compel you to assume, then, that you want to live in a ultra-low mass red dwarf system because you think, wow, the star will essentially live forever. This is an interesting topic, and this is one of the last things we'll talk about tonight. We are concerned that red dwarf systems are actually very dangerous because red dwarfs tend to have unstable electromagnetic fields, which leads them to produce a lot of solar flares. These are X-radiation events, very bad, very high energy electromagnetic events that could strip planets of their atmospheres or radiate their surfaces too much. So just because your star is long-lived doesn't mean you want to live around it if the star has a volatile surface. Red dwarfs tend to have very volatile surface activity. In fact, there's a type of star known as a flare star, and these are stars that have lots of really huge flares, and they're often red dwarfs. Yeah. Any questions about that? All right, now, someone asked a very deep question, and this kind of lends itself to the finale of the show, so to speak. When a planet goes in front of a star, we have an opportunity to do some useful science. So let's say this is the planet transiting the star. Right here, something exciting happens because the starlight is actually going to filter through the atmosphere of the planet. And this allows us to study its spectra. And this allows us to look for interesting signs of unusual atmospheric composition, or maybe even signs of life if you want to be really optimistic. It turns out that we already have the technology to do it. We've already begun sampling the spectra of the atmospheres of some exoplanets. And much to our delight, it turns out that some of them are host to things like water vapor, which would indicate they probably have liquid surface water. That's a huge deal. Again, does that mean they're full of alien life? No. But just having surface water in abundance is a big deal when it comes to searching for alien life. Now, you may have heard of the extremely famous Kepler Space Telescope, the extremely famous James Webb Space Telescope, which is hopefully going to launch at the end of this year. James Webb will have sufficient resolution to study lots of exoplanet atmospheres, and we're going to look for unusual things that might baffle us. Here's a random picture of an exoplanet system. Kepler 452 here is that super Earth I talked about earlier, so there's the big Earth-like planet. Notice that Kepler 452 and Earth have very similar orbits. They have very similar years, and they orbit stars that are very similar. So Kepler 452 is actually a sun-like star. This would definitely be a system we'd want to study the spectra of. Maybe Kepler 452b has, for example, water vapor on the surface, or maybe even stranger things. Notice Kepler 186f is a red dwarf system, and its Goldilocks zone, which is, by the way, what those green disks are smaller. But we find planets within those Goldilocks zones all the time. But like I said earlier, red dwarfs might not be the best place to live because of radiation output of their stars. We're still working on that. We're not sure about that. Now, let's finish up with this thought. If you were studying an exoplanet system, and you were studying the atmosphere of an exoplanet, you know what would be more exciting than water vapor? If you found something that didn't make sense. If you find an atmospheric composition that cannot be explained, that means something weird is going on. In the case of Earth, if extraterrestrials were studying our planet, they would be baffled by the abundance of free oxygen. Some of you probably learned in grade school, hopefully most of you, that Earth's atmosphere is unusual because it has such a great abundance of free oxygen. Now, when I say free oxygen, oxygen is highly reactive. It tends to readily form oxide molecules, and so it's sequestered out of the atmosphere by rocks, like, iron oxide is rust, for example, and you have silicon oxides. There's so many oxide molecules. Carbon dioxide, that's another one. So, who can tell me, why does Earth have so much free oxygen in its atmosphere? Anybody? Why is there so much free oxygen in Earth's atmosphere? Please, grade school students, tell me. Why does our planet have so much? Plants? Well, what do plants do? And by the way, the answer is not just plants, but you're not wrong. What do plants do? Trees? Oh, okay. Well, those are also plants. What do they do? What mechanism do they employ as part of their life cycle? Biology. Oh, well, they don't turn CO2 into O2. They break the molecular bonds. They sequester the carbon, and they release the oxygen back into the atmosphere. They don't create oxygen. They free the oxygen from the oxide molecules. Yes, and that is the process of photosynthesis. You guys might be aware it's not just plants. There's also photosynthetic animals, like phytoplankton, for example. Earth's oceans are filled with microorganisms that employ photosynthesis to glean energy from the sun and power their useful chemical reactions. So, if we were to find an exoplanet system which had an atmospheric composition that couldn't be explained, it would imply that some mechanism was at work, perhaps the mechanism of life. By the way, it doesn't necessarily have to be oxygen. It could be something else. But the point is, it has to be weird. So something strange is going on. We have a pretty good idea, we have a pretty good understanding of why planetary atmospheres are the way they are for natural astrophysical reasons. So if we do find an atmosphere which is bizarre or baffling, again, very exciting. Any questions about that? All right, we went a bit over time, but I think this was a fun topic. It's one I certainly enjoy talking about. So let's do 7 minutes, 8 minutes. Let's do 8 minutes of questions, and then I'll end the show. Question and answer time, my friends. Here's your chance. Ask those burning questions. I'm waiting. I'm gonna read the moderated chat log while you guys are reading. Let's see. Can exoplanets be seen through amateur telescopes? They cannot be seen. However, believe it or not, it is possible to measure the drop in brightness of a star. You wouldn't see it with your eyes, of course, but with high dynamic range sensors, it could be detected, yes. So you could do actual useful exoplanet science with off-the-shelf equipment, but you wouldn't be able to look at them. That's a good question. Let's see. Gas giants close. How hard is it to determine the strength of gravitational lensing? We just measure it. So. Oh, that's a great question. Does microlensing work in any wavelength other than visible light? Of course. And so there's even X-ray microlensing, for example, that we've detected. I mentioned earlier, we've actually found exoplanets in other galaxies. And some of the effect is resultant from X radiation being bent by the gravity of things. That's a good question. I'm looking at the list. What is the noise in the star brightness measurement versus a drop in brightness from planet transit? That's why we stare at the stars for in ideally multiple years, so we can filter out the noise, so you can tell if an event is real or not. Yeah, that's a good question. Still got 6 minutes. Have all the exoplanet systems conformed to single ecliptic plane? No, we've actually found exoplanet systems with multiple planes of ecliptic, if you will, because it's a multi-star system where their planets do not agree with each other's planes. And by the way, again, that's an example where that can actually be a helpful problem because they affect each other in weird ways, which we can detect. That's a good question. So yeah, we have found multi-star systems with multi-planets that orbit differently So you have one star with an ecliptic plane like this, and the other star has an ecliptic plane like that. Yeah, for example. Oh, hey, so you know what? That's a deep and very important and profound question. Someone asked, why are Venus and Mars in the Goldilocks zone? So one of the most annoying and persistent myths that I deal with still, and I've been dealing with it my whole life, is this notion that the Earth is in the perfect spot for life. If we were a little closer to the sun, we'd all burn to death. And if we were a little farther away, we'd all freeze to death. It's completely wrong. Earth is a nice place to live, not only because we're in the Goldilocks zone, but because of the composition of our atmosphere, which is thick but not too thick, to set up a strong but not too strong greenhouse effect. And we have a strong magnetic field, which protects the composition and the density of our atmosphere. So Earth is a nice place to live because we have the right atmosphere, we have photosynthesis, and we have a magnetic field that protects the atmosphere. Now, in the case of Venus and Mars, Venus could have been a nice place to live, and so could have Mars, if only their atmospheric situations were different. In Mars's case, it gets quite interesting because we know that Mars used to have a thick atmosphere. We know this because we know that it used to have liquid water on it. We know that Mars used to have a magnetic field. Once the field collapsed, the sun was able to strip Mars of his atmosphere almost entirely. Mars's atmosphere is only 1% as thick as ours because the sun has robbed him of it. The reason this was able to happen is because Mars's magnetic field collapsed when his core solidified. In the case of Venus, Venus is much heavier than Mars, has almost identical mass and gravity to the Earth. So Venus is able to hold on to her atmosphere much better. But because, again, she lacks the protection of a strong magnetic field as well, the sun has been able to strip Venus of her lightweight atomic gases, leaving only heavy molecular gases like carbon dioxide, which creates this runaway greenhouse effect. So Venus is a horrifying, hellish wasteland of intense pressure, 90 bar pressure at the surface, so it'd be like standing on the bottom of the ocean, 900 degree Fahrenheit temperatures. By the way, hotter than Mercury. Mercury is closer to the sun, but it's not as hot as Venus because it doesn't have a thick atmosphere to trap infrared light from the sun. And then Mars, opposite problem, too little atmosphere, too thin. It has a cold, desiccated, radiation-soaked surface. Both planets are pretty crummy. Earth is pretty nice. You should be grateful for Earth. You are explicitly an Earthling. You know, we're so immature in our need to run away from Earth, but I think it's a pretty nice place to live since we literally evolved to suit it perfectly. It's not that Earth is nice for us. We became part of it. We are Earthlings by definition. All life on this planet has adapted to the conditions on Earth that we take for granted, but are by no means universal. Nothing about Earth is universal. And that's a big deal. And by the way, that fits nicely. That concept fits nicely into the context of exoplanets, because we learn that things that we used to consider normal are not. And there's all sorts of variability in the universe when it comes to atmospheric composition, mass, gravity, day length. Oh, that reminds me. I forgot. Let me show you something. Hold that thought. I want to show you the unusual thing about TRAPPIST-1. Because TRAPPIST-1 entails planets that are very close to their parent star, all 7 of these worlds are tidally locked to TRAPPIST-1, which means they have permanent day sides and permanent night sides. There are no planets in our solar system like that. There are no planets that are tidally locked to the sun in our solar system. However, there are tidally locked moons. For example, Jupiter's moons are tidally locked to Jupiter. Some of them, not all of them. So imagine that, a world with a permanent day and a permanent night. Who knows what it would be like to live there? You might have this band of habitability going around the world on the terminator between day and night. And, you know, that might be where you'd live, if so to speak. So you might have this, they call them eyeball worlds, where, you know, we have this blazing hot desert on one side and a frozen wasteland on the other, and a nice place to live in between. Who knows? That's an interesting thought. That's not something we can relate to in our solar system. Questions? Here's a nice drawing of TRAPPIST-1 and its little baby planets, which orbit its tiny little star. I'm going to put the picture back that I liked, just because I think it's a delightful picture of the strange worlds orbiting a neutron star. And we have 1 minute left. Someone answer. Or someone ask questions. How can you tell if they are tidally locked? Because they have to be. That's actually an interesting question. That's a mathematical question. We can tell if a body is tidally locked without actually measuring it to be so if it's within a certain radius of a certain mass body. In this case, they must be tidally locked because they're too close to their star not to be. That's a good question. All right, it's 8:25. That was the time that I kind of indicated will be the cutoff. That was a good. You know what? There's been a lot of great questions tonight. You know, someone asked why the light from the Einstein ring looks like a circle. It's just like if you have a glass ball, light will bend in complex ways around the radius or the perimeter, the edges. Believe it or not, that's actually an optical question. That's optical science, understanding why the light will become a ring. And that gets more difficult as we start to deal with extremely, extremely high gravity, very compact objects like black holes. You may have heard that it was noteworthy that the movie Interstellar, and by the way, I hate that movie, but that movie did provide an accurate depiction of what a black hole might look like. And it turns out it takes some supercomputer simulations to render the bending of light accurately when you're dealing with such a compact and heavy object. Yeah. Exoplanets affect gravitational waves. I mean, the answer is technically yes, although we'd probably never detect it even with the most sensitive detectors because planets are just such low mass objects that they have very little effect on the curvature of space-time and mass. And so that's the reason why all gravitational waves so far detected have been resultant from hypermassive objects like black holes and neutron stars interacting very closely. So no, you would not likely detect gravitational waves from planets, maybe in some far distant future when we invent like ultra sensitive gravitational wave observatories that are space-based. But no, we can't really detect gravity waves from planets. No. All right, you guys have been great. This is a great topic. Like I said, I kind of love it. And I'm going to start signing off. The next week's show is Elusive Mercury, How to Catch a Glimpse, because I don't know if you heard, Mercury will be in a very well placed to observe next weekend. So keep that in mind. And after that, on the 31st, we'll be talking about Goldendale Observatory's history a little bit, so that might answer some of your questions about our facility and also solar eclipses, which are part of our story. So again, thanks so much for your time, my friends. If you had fun tonight, please like and subscribe. Tell your friends about us. Spread the word. And I will see you next week.